All right, cool. So, hey everyone. Today's lecture is going to be on Keras and convolutional neural networks. But before I get on to that, we have released the project. Many of you may have seen it on Piazza. And so this is a pretty involved project, but it is the last project for the semester. So you have about, I think 3 weeks to finish it. It's due on May 1st. It's definitely a little involved. You have to make three separate kind of models for classifying a set of data. But that shouldn't be too terribly difficult. You can pretty much use all the sklearn libraries that we've shown you guys, plus anything that you find on there, as well as any neural network stuff that we show you in this lecture and the previous lectures as well. So yeah, make sure you start early. It can be pretty. It can be a lot of work if you're pretty new to programming and everything like that. So make sure you have enough time to ask questions. Okay, so today's agenda will be first starting out with building a neural network with Keras, where I'll get to that in a second. And then I'll talk about convolutional layers, which build up to convolutional neural networks, which are basically the state-of-the-art for pretty much all machine learning these days. And then finally, I'll talk about building a convolutional neural network in Keras. Cool. So the first thing I'm going to do is just demonstrate how easy it is to use Keras. And so this is something that I made like literally in the past 10 minutes. And basically all it does is it classifies MNIST digits. So Keras is very nice. It comes prepackaged with a lot of little helper functions here and there. And so this includes something like the MNIST loader right here. So basically I can just load the MNIST data by calling this simple function right here. Let me just make sure it's visible. Yeah, the simple function right here. I reshape it. I create the model very simply here by creating the sequential thing. Basically, it just says like where we're going to put all the layers of our neural network. I grab some layers for this neural network. So the dense layer is the same thing as the fully connected layer. This is actually what we've taught you before. All these these layers where every single neuron is connected to all of the neurons in the next layer. That's just your dense. We have our activation function, which should have been brought up in the past 2 lectures as well. Basically, just what the nonlinearity we apply to our values. And then I add another dense layer. Actually, I'll add one more. And then I'll add one more activation function.
What was the argument
for the activation function? Or for a model?
200, for example.
Oh, okay, yeah. So dense 800 basically means that's the number of hidden units we have. So I could draw this really quickly.
Oh, okay.
And so let's say you have an MNIST image, which is a 28 by 28 image. To pass it into a neural network like this, a fully connected neural network, the ones you've seen this entire time, you have to vectorize it. So that means you have to transform this like 2D matrix into a 1D vector. And so that just means that you just like put them all, you just stack the rows of the image. And so you end up with a 784 length vector. And so then you feed this into your neural network. So this 784, you can see it's the input shape, right? Makes sense. And then you have your hidden layer, your first hidden layer, which is going to be of size 800, basically just 800 units. That means that we have like 800 lines connecting from each of the vectors from the 784 initial vector. Sorry, each of the elements of this initial like MNIST flat image thing. And then we apply a ReLU. So basically we just apply the softmax function. Not softmax, my bad. The function max 0x, whatever. That's just the ReLU function. And then we apply that to all the elements here separately. And then we take another layer, this time size 200, and yeah, we pass the values into here. And I'm actually missing one more layer as well. So we probably want to output. So this basically transforms the data from, I'll get to that in a second. And then we have one more layer that has 10 dimensions. Yeah, so what this basically does, it takes a 784 vector, it transforms it into 800 dimensional space, basically just 800 values by this matrix multiplication.
Where do the extra values come from?
Where do the extra values come from? Oh, so you can imagine this is just like a matrix operation.
Oh.
So it's like, if you remember from 54, what would it be? So let's say we're like left multiplying a column. This is like 784. So 784. It's just the dimension of the matrix that we have here. Make sure, yeah, this is right.
Oh.
Right. Okay.
Okay.
Yeah. So basically, it's just the matrix that we
Oh,
multiply
I see.
by. And so that's all a layer really is. It's just like a matrix that we take the matrix product with. And so then we pass that through the 800 layer. We apply the ReLU just on every single element. Fairly simple. And then we apply a 800 by 200 matrix. Sorry, 200 by 800. Imagine this is 200. This is 800 now. And then this is our vector at this point after we've applied the ReLU. And that gives us out a 200 size vector. And then we apply one more layer that should, we apply one more ReLU, more nonlinearities make it better to learn. And then we apply one more layer that transforms it from 200 to 10. So that basically we transform it from our image representation, which is 784 dimensional, to a representation that can account for every single possible digit. So that's why we choose 10 out here, because there's a spot for every single possible digit. So let me just add that here and just show you, hopefully, that it trains. Whoops. Sit down. Okay. Something's wrong. Expected dense 7 to have shape none, but got an array with. Oh, what? That's so weird. Oh my god. Okay. Yeah, no, I did have to rerun some stuff, but I just have to one-hot encode this vector. Let's see. There's a fast way to do this. Google it. One-hot encode numpy array. Nice. Yes. If this doesn't work, then I'll just go on with the lecture. But I think you'll get the main idea, because we have another homework that comes with it. Ah, there we go. I think. Okay, maybe that'll keep running. Hopefully something will happen, but whatever.
It's 3 different sheets.
Yeah, so I want to talk about Keras for a second. So Keras is pretty cool. It makes making a neural network really easy. So if you remember, we were talking about a lot of complicated like gradient stuff and like calculating the gradient when we do backpropagation and all these like different steps in the neural network training algorithm. Well, the nice thing about using something like Keras, using this high level language, is that you don't have to really worry about actually calculating those explicit values. In things like Caffe, you may be required to do stuff like that. Caffe is actually like kind of an older deep learning framework that comes out of Berkeley. You'd have to like think about all these like gradient stuff and like going through all these steps of figuring out really complicated mathematical operations. Even though it somewhat simplifies it for you, you still have to think about it. Keras, you just let it run, and it takes like really no time at all to create the network, so you can focus on debugging the issues with your network, and then instead of having to worry about implementation. Cool. So as I mentioned before, what we've basically taught you for the most part is fully connected networks, neural networks. That means that every single neuron in every single layer, let's say in a single layer, connects to every single layer in the next layer, basically by some weight connection. So that means that data that goes, you can think of it like a circuit where you have data traveling along these edges here, and then you have to spread your data out from every single neuron's data goes to every other single neuron's data in the like later parts of the network. Now this poses kind of a problem. You can imagine that we're going to have a lot of weights, right? You can imagine that because we connect to every single neuron in the next layer, you're going to end up with many, many different weights. And so in this simple 3 by 4 by 4 by 1 network, we end up with something like 32 weights. That's okay. Like, that's not bad. But this network is like really unrealistic. You're not going to solve any problems with it. It's not super important for anybody's research or anybody's like application in industry. Now, if we wanted to do something a little bit more complicated with what I was trying to demonstrate in Keras, but unfortunately didn't work out, this is probably closer to a practical example. So we have our, say, 784 dimensional vector, the flattened MNIST image, and then we have our MNIST network, which I was trying to replicate. Oh, I know where I went wrong. Okay. So basically in this network we have, instead of this extra 200 layer, we skip this 200 layer, and then we go straight to the 10 layer, to the 10 dimensional layer. And so, yeah, in this case, you start seeing the number of weights explode. So by calculations, 784 inputs times 800 hidden layer neurons plus 800 hidden layer neurons times 10 output layer neurons gives us a total of 600,000 weights. Now, your computer right now could handle that fairly well. I wish I could get Keras to show you how like quickly it actually runs on my computer. It's not bad. It works fairly well, but like the previous network, this is actually still kind of a baby problem. It's still not very representational of like the more difficult problems that you would want to solve with a neural network, and that have been solved with neural networks to like amazing results. And you can even better illustrate this by the fact that you can deal with like much larger images, greater than MNIST, because MNIST is such a small data set. Like you can see the pixels, right? You can see the pixels of this image, so clearly it must be very, very small. Additionally, when we do our vectorization of our images, we lose all the spatial information. So whereas we'd have like a nice handwritten 2, we know that this like corner here is close to this curve here, and then this like indent here is close to this end here, whatever. You don't have that information anymore once you vectorize it. You completely lose it. And so you have to sacrifice that information to use a fully connected network. Now, you have to ask the question, like, can we do something better? And like, does our brain do something better? And in fact, it does. And so, before I get into that, I want to just demonstrate the problems with, vectorizing an image. So basically, let's say these are 100 by 100 pixel images. That ends up with like a 10-dimensional vector when we flatten it to put into our fully connected network. So that means that if we only had like one hidden layer in between our initial image and our output, and we were trying to classify dogs and cats, we would require 8 billion weights to classify a dog or a cat, and that's not even realistic. Like that sort of network with only one hidden layer won't actually do this anyways. Instead, you'd probably need multiple hidden layers to actually properly separate the image into the respective cat section and the dog section in like the crazy weight space that you deal with in neural networks. And that's problematic. Like 8 billion weights starts becoming like a huge is really taxing on your computer. You'd need like hardware. You need like crazy hardware to actually do anything properly, and basically people wouldn't be able to solve any sort of problems. So as a demonstration, I should also note each image not only has the physical dimensions, the width and the height, but it also has this extra dimension related to the color channels in the image. So if you've encountered that in like Photoshop before, you've seen like the RGB images, you have to store that image data somewhere. And so when we implement this, when we feed images into neural networks, we have to account for this extra dimension to actually get any reasonable results. And so not only are we dealing with we're not dealing with 10,000 vector size vectors. Now we're actually dealing with 30,000 size vectors. And so as you can see here, we lose all of the spatial transformations from before. And it's basically, you can't really tell what's going on in this by just looking at it. So our solution is to use convolutional neural networks, if you didn't guess before. So here's an example of a convolutional neural network. I think this is from one of the, not sure if this is one of the earlier ones, but it's from one of the earliest adopters of the convolutional neural network, Yan LeCun. So the basic idea is we have like multiple convolutional layers, which I'll get to in a second, and then they eventually connect to fully connected layers that we did before. But these convolutional layers are just basically efficient ways to downsample and like interpret the concepts contained within an image so that we can more efficiently run it through our final fully connected layer, fully connected network. So a convolutional neural network has a set of different layers, pretty much an extension of the fully connected network that you guys were introduced to before. So the first one's very clearly obvious. It's just input. That's what we've been dealing with all the time, your standard machine learning input thing. The next layer is the convolutional layer. This is really the meat of the convolutional neural network, and it's what really makes the the network itself learn anything cool and creates so many solutions for many different types of problems out there in like computer science and stuff like that. Then there's the activation function. You should be fairly familiar with that. That's like the ReLU that I applied here, or the sigmoids that were introduced in previous lectures. Then there's a pooling layer, which I'll get to in a second. And finally, fully connected. This is just a standard piece of a convolutional neural network. There's usually a fully connected layer, or a few fully connected layers at the very end to make like the final processing into a regular vector form, which most labels are typically just vectors. Okay, so our input, 100 by 100 color image with 3 channels. So you can imagine it kind of looks like this, and they're separate channels. And that means, and another piece of terminology is that we actually tend to view images as volumes instead of flat like images. And as you can imagine, that's because they do have this like extra third dimension that you typically don't really perceive when you're looking at an image. But we usually account for this this third dimension because it makes it easier for what the convolution layer does to an image. It does to data, really. So the convolutional layer. What this basically does is it takes in a volume. So in other terms, this is a 3D tensor. Don't worry about that terminology. It's a little bit out there. But it's a 3D volume of data. And we apply this thing called a convolutional kernel or a convolutional filter. I'll flip between the terminology, so just make sure that you understand that they're both the same thing. Filter and kernel equal to each other. And you basically take this kernel or filter, and you just put it over a piece of the image, and then you take the dot product of that kernel's data, like numbers, with the data stored in that like place that you're hovering over. So as you can see in this image right here, you have your square at the top left, where the filter, the like square in the center, is hovering over at the moment, and then we take the dot product of all those values, and so we're left with -8 because all the values just multiply it, go out to 0, except for the bottom right corner of the filter and the source pixel. And then we get the final value out into this other volume, this other data that we deal with, similar to how we had like a different vector space in the neural network, or in the fully connected neural network example. Let me see if I have any notes on this as well. Okay, so does anybody have any questions about this first? Okay, so yeah, these filters, as you can imagine, actually preserve more spatial features now. So basically, we just add like a two-dimensional aspect to the way we're computing all these values in the later data, similar to how we like pass through the network. Basically, data that's passed through the network now has information about what's nearby. And but clearly that's going to add to our accuracy, because now with like any extra information, even in the form of just like the structure of how we lay out our data, is going to just add value to our network. And so, I guess I didn't really cover this well enough. So you take this filter and you basically pass it over the image entirely. So you take these things called strides. They're basically just like simple steps through the image, and you just take this dot product filter, the dot product of the filter and the image that it lays over. So our convolutional layer has a set of hyperparameters. Basically, we have our filter size. So as you can, oh, hey, what was your question?
How do you choose like a filter? Like what do you choose, like coordinate?
Oh, are you talking about the data in here, in there? Yeah. So actually, that's the key thing that we do in all neural networks. We just learn them. We just run gradient descent, and then we're able to find the values that best work for that, basically by minimizing the error at the end of the network. And so backpropagation just lets us discover that, and it translates very nicely. So you can go through and do the math if you want to. Now, as I mentioned before, Keras does a lot of that stuff for you through like TensorFlow and like all these other layers that it uses in its computation. Yeah. So as I was talking about before, there's a set of hyperparameters that come with the convolutional layer. There's the filter size, which is basically the dimensions of that kernel filter thing that I was talking about before. So we could choose to have this as like a 4x4 filter instead of a 3x3, or like a 2x2 or 1x1. Really doesn't matter. I mean, it does, but like we have the option to change that around. But a key thing to know is that these filters are actually 3D volumes themselves, and so they will match the depth of the input that you get. So let's say we're dealing with our like standard image input. So it has like width, height, and then 3 channels for RGB. Our filters will also have 3 depth, but then their own like kernel height, kernel width. So K width, and then 3. And so this just means that they have 3 times kW times kh values stored within the filters. And additionally, in our convolutional layer, we may have many of these filters. And so this actually corresponds to the output volume of what we receive. So I guess I should take a step back and explain like how a single filter processes the data inside of an input volume. So let's say we only had one filter in our convolutional layer of size kh, kw, and then the depth, of course, matching the depth of the input volume. This is going to output it's going to output a volume that has some function of, or a volume of depth 1. And its dimensions are going to be some function of its kernel width and height, plus like the stride that we use to traverse the image. Now I'll get to the stride is the next thing I want to talk about. Basically, it just means the distance that we like travel every time we move the filter. So a good demonstration of that is on this next slide here. we basically just move over one pixel every time we, I guess, convolve, you could say. And so, yeah, this is equivalent to a stride of 1. And so you can imagine if we just set our parameters to, we can actually modify our stride parameters for not only like the x direction as demonstrated here, but we can also modify them for the y direction. So you can imagine that we could move, we could have a stride of 1 in the x direction like we have here, and then we could also just skip a stride and go to a stride of 2 for the y direction. So it's as if we go to the second row after we finish this this row's convolutions.
Is the green layer the output of the filter?
Yes, the green layer is the output of the filter, and then the filter is the grayed out piece. Yeah. Any questions about that?
So you apply a filter to like subsets of an image to create a new image in a later layer.
Yeah, exactly. And it in a convolutional layer, as long as the kernel height and width are greater than 1, it will reduce the size of the volume. It'll reduce the size of the, it'll reduce the area, I guess you could say, basically the face of the volume. But a key thing to note is that we can have multiple filters, right? We can just run multiple filters over this data. And so that means we can actually accumulate more and more slices of a new output volume. And so our new output volume, after we run our whole convolutional layer with like its set of filters, is now going to be some function of the kernel width and height plus the stride and like minus height width. I don't really know that off the top of my head, but the depth will be equal to the number of filters that we use. So, yeah.
And what's the purpose of like having a stride length less than your whatchamacallit, the size of the gray stuff? Like why do you want to overlap?
Oh, why would you want to overlap?
Yeah.
Because you may want to capture details like you may want to capture like correlation details between, I don't know, let me give you like a very simple example, like 5 by 5. 2, 3, 4. Yeah, so you may want to capture similarities and details for this pixel and this pixel, and if you have a 3 by 3 filter, and you were just to skip, actually it's not a good example, let's say I have one more. So let's say you have a 3 by 3 filter, and you don't overlap the filter, then you won't know that these 2 points correlate, but they do happen to correlate. But having this overlap means that you can incorporate this correlation between like 2 different points.
And by correlation, you mean just some kind of similar feature, like color or shape or whatever.
The convolution function effectively kind of captures this idea of a correlation by, I guess, just convolving, really.
Okay.
Any other questions based on that? Yeah.
Is the only way of like convolving by taking dot products, or is there like other methods?
Like technically, what I think most implementations do is they'll transform it into the Fourier domain. So like frequency space and stuff like that. You may have seen it in 16b, EE16b. Oh, if you haven't taken it. Oh, okay. So this is like a signal processing technique. And what it allows you to do is it turns out the convolutional operation just transforms into multiplication in that domain. And so, yeah, you can do that, but it's actually the same thing mathematically. And it just can be more efficient because transferring to Fourier domain is rather fast. Like there's a fast algorithm for it. So, okay, so as I was talking about before, convolutional layers output a volume. And so in this case, we have a convolutional layer with 6 filters, and so it outputs a volume of depth 6. Cool. And so an example of a convolutional filter in Keras would basically be we can set it up like this. We have 10 filters. Our kernel size is equal to 3 by 3, and then we set our stride to just 1 by 1. And so that matches the parameters listed here. And so, here, I actually have a calculation of the output volume. Oh, whoops, that's wrong. So imagine the input volume is not 100 by 100, but 300 by 300 by 3. Then you would get this output volume with these respective parameters. So it's something like kernel size minus 1 plus like or yeah, volume minus kernel size minus 1 or something like that. I Google it. Let me see if there's anything else I wanted to add to this. Cool. So the next layer you've seen before, activation layer. In deep neural networks, we tend to like ReLU layers, simply because they're very, very easy to compute. You can imagine that it's like if you have a linearity, literally a linearity is copying a value. So computationally, that's very nice. And then taking the max of 0 in that number is basically just saying, is it positive or not? And that's a fairly easy operation to put onto a computer. So that just makes it more efficient to calculate, basically run data through your neural network. Let's see. Now, of course, we can use other things like tanh and sigmoid, but those suffer from issues with like numerical instability, and that like when you start getting into the later parts of the sigmoid function, let's say you end up with the data over here, it's just going to level off in the sigmoid function. And same thing with the tanh, it's also a very similar function. So this has many, many benefits, and it's simple. So if you ever heard of the principle of Occam's razor, it very much applies in this case. Cool. So I guess the third type of layer that I want to talk about is called pooling. And this is, again, kind of a feature of convolutional neural networks in that you probably haven't seen it before. The basic idea is that it's just downsampling. It's not crazy, but it operates in a similar function like method as convolution. Basically takes an area of the image and applies a certain function onto it. They're called like aggregation functions. So typical functions that are used are like max, the maximum of that area, or the average of that area. And so this just allows us to like summarize all the data that's contained in this area that we go over, and put it into, I guess, a condensed form. So as you can see here, this is a max pool with 2x2 filters and stride 2. So this means that there is actually no overlap in the filters that we use in compared to the previous example with the convolutional layers. But these different colored areas are just the areas where we apply the max pooling operation. And so in this top left corner, we take the max and it's 6, top right corner it's 8, and so on. And so to implement it in Keras, just add this. Any questions about that? So the nice thing about this is it just makes our data more easy to deal with, I guess, in these later layers. And you may think like, oh, we're losing all this data as we progress through the network and we go through these max pooling operations. But the nice thing is, because we're learning as we like so we pass all the data through the network, right? But we also are performing this like back propagation algorithm and updating the weights along the way. We're actually making it so these max pooling operations are like funnels into our data. And so they allow you to do this kind of like dimensionality reduction, and thus making it easier to transfer data and like force data into nice spaces, vector spaces, or manifolds, if you will, that are really easy to deal with mathematically, and thus we can produce pretty cool things with like pulling out cool images of dogs, or like classifying dogs very correctly, or other things like that. All right, and the last type, fully connected. Mentioned this before. I've brought this to the ground. Very simple model, dense units. Now we typically just add this at the end of a neural network, of a convolutional neural network. It's nice because it gives us vector outputs, whereas the convolutional layer would typically give us volumes. And vectors are pretty much closer to what we want to deal with when we're dealing with like labels. So if we were in the MNIST example, then our labels would probably be vectors, of 10 dimensions, 1 for each digit. Or if we're using a convolutional neural network on something like ImageNet, which has like 1,000 classes, it's a lot easier to represent that as like a 1,000-dimensional vector at the very end of your network than it is like some convolutional operation. Okay, so just some quick math. Just to really drive the nail in about the advantages of convolutional neural networks over fully connected neural networks. So let's say you have a neural network that has 30,000 neurons as input. This is the same thing as the 100 by 100 color image going into a neural network, and a hidden layer of size 1,000. Does anybody want to guess how many neurons are, or how many weights are required in that case? Yeah, exactly, 30 million. And so, yeah, and then the same filter in a convolutional layer, which requires, which would take like 128 filters, which is like rather standard size, each of size 5 by 5, basically dimensions 5 by 5. That would only require 9,600, so we just multiply 3 by 5 by 5 by 128. And so you can see the improvements pretty drastic in a single layer. So the last thing I want to talk about is what a ConvNet learns. Should be fairly brief. Yeah. So ConvNets are super cool because they mimic the brain very closely. I think we talked about the Wilbert and Hugh Bell, or Hugh, I can't pronounce their names properly because I don't really know them. But there was that one image or that one video where we watched like a cat looking at a looking at some screen where there was like a bunch of dots and stuff. And then they were trying to get this cat to, they were trying to see whether the cat's brain would be signaled or like would release a signal when looking at these images of dots and stuff. And they couldn't get any results until they finally just like showed the edge of the paper to the cat, and then suddenly the cat's like brain just lit up. And that's because they were looking at the earlier layers of the brain, of the cat's brain. And the earlier layers of the cat's brain are really good at perceiving things like edges, gradients, and stuff like that. And it so happens that when we train a neural network to recognize images, I think this particular neural network where we grab these pictures from is trained on ImageNet, which is like classic neural network image classification challenge. We can see that it actually learns a very similar set of function, or a similar set of filters that the cat's brain likely has, or that likely has as well. And so you can see here that we have a bunch of edges as well as these gradients shown right here. And so these compose the lower level features that a neural network would learn in the first few layers of its of the neural network itself. And so what happens is, you can imagine we have all these like edge detectors basically at the very beginning. We can compose those together and we can get a little bit more complicated structure. So in the mid-level features, once we've composed all these together, you start seeing things like edges, corners, curves, and even things like circles and something that looks like kind of an eye here. And then from there on, we can imagine that we can compose these even further and get more complicated structures. If you look kind of closely, you can see there's like a honeycomb here. Looks like there's a bird's beak. I think there's like a wheel up there, and all those kind of cool things. So as you can see here, the neural network just really responds to this like constructed data that goes through the network, basically. Yeah.
What types of things would it learn for like non-image?
Non-image stuff? I don't know. I haven't really looked into that much, personally. I imagine, yeah, that's really hard to say. That'd be interesting to check out. Because this is a pretty standard structure for what your brain kind of looks like. This hierarchical buildup of data and stuff like that. So you can imagine that maybe some musical data would also produce something very similar like that. It'd be worth checking out. What's up?
Does this work for like teaching a computer to read or something?
Teaching a computer to read?
Yeah.
Oh, you mean like build up features like that?
Yeah, like just like had it like read a book or something. Learn how to read that.
So you could get it to like read a book. If you want to do anything crazy like comprehension, that's pretty much out of reach, because in the brain, this part of your brain composes like such a small part of the whole volume of your brain that like you're really missing the key comprehension pieces that would be necessary to like really understand what's going on. You can get it to, you could probably make a neural network that like reads in a book, takes in this like text data, puts it out, and then can comprehend, then like can maybe summarize the data. But it won't know what it's doing. It's learned just a function that maps. Now,
is that how like the the Google Maps thing where you like look at something.
Yeah.
Or not Google, it's Google Translate thing where it translates.
Yeah.
Is that something like this?
It's totally a neural network in there. Yeah, they probably use something bootstrapped off of a later version of this kind of network. They're called ResNets, if you're interested. They're basically like, these networks are like maybe 20 layers deep or something. The ResNets are like hundreds of layers deep. And so they seem ridiculous in implementation, and they're like, the only way you can actually train them is if you're Google or Facebook, where you have like access to an enormous amount of cash flow to like train a huge neural network across many different GPUs all at once. But it ends up being really good, and it turns out you can actually use that for a bunch of different applications. Once it's already learned, you can like adapt it for a bunch of different things. So that's actually, it's kind of an interesting topic. There's this like idea that you can take a neural network that's already pre-learned to do one task and actually adapt it to do another task by like slight variations. So let's say you have your neural network here, and you train it to classify images or something like that. You can use it to discriminate, let's say, or like a key example that I've seen before is like you can take that and apply it for like videos and get it to recognize videos fairly well, even though it's not originally trained to understand what's happening inside of a video or even taking the data from the video. So that's called transfer learning in the like deep learning research field. It's a pretty big area because it's very critical for how we as humans learn things. We end up like trying to draw lines and connections between abstractions that we made in one field to another field, another domain that we're trying to learn. Very interesting, very key place where we'll probably find results in like advancing towards general artificial intelligence. Yeah, definitely worth checking out. Oh, back to the representation stuff though. So we can actually use these representations to do cool stuff like neural style transfer. So this right here was originally an image of, I think, San Francisco, and somebody took the style of Scream, passed it through a neural network similar to the one that was used to create this, grabbed out a later grabbed out a like neuron late in the layer, so like deep in there, and then grabbed another neuron, or passed the original image here, the original image of the like San Francisco skyline, and then they grabbed another different part of the neural network, and then they could just combine them together using these high-level representations, and was able to effectively copy these the artist's style onto this image. And so, yeah, that's just a cool thing that I thought was interesting. So I listed one more resource here on convolutional neural networks from the Stanford Neural Network course. I think it's pretty good. I'm going to throw on some more when I upload the slides later today. Does anybody have any questions? Cool. Okay, so we made a Keras homework that I think it's going to be due next Monday. It should be fairly simple. It's mainly just to get you to walk through what happens inside of Keras and like building a neural network in there, because we do want you to use at least a single, or at least try to use a neural network for your project. And so we hope that this Keras guide is sufficient enough for you to really understand what's going on there. I hope it's as simple as we tried to make it. Of course, if there's any problems, post on Piazza, email us, come to our office hours, all that jazz. Yeah, I can maybe whip up a convolutional neural network fairly quickly, or just find one. Actually, I probably have one.
Wait, is it on GitHub?
Where the
Day 15?
no day 16 is the homework is in homeworks in the folder in
Oh.
homeworks. Yeah.
Okay.
Let's see. Code. Okay, let's see. Hopefully this works. No. Let's see what this does. Okay, so I think I already have some code here. Oh yeah, this demonstrates the Keras neural network with just the dense layers. So you can see here we have our output dim of 800, our 800 hidden layer, and then our 10 output layer here. And I actually had a softmax activation, which is very similar to the sigmoid, except for it basically just outputs values that are between 0 and 1. And so that the entire vector is sums up to 1. So it gives you basically like a probability distribution over every single possible digit. And then training is fairly simple. So once we've added all the layers to the sequential model, we just compile stuff with our loss. So categorical cross entropy is just like a standard loss used for like probability and stuff like that. You'll read into more of that if you take 189. Our optimizer is standard gradient descent, and then we just choose an accuracy metric. And then we run our fit, and so the interface is fairly nice. It just says how many epochs we want to do. Epoch is just the run-throughs of their data. Shows how fast you're doing everything, how good your loss is. Basically, your loss is not an accuracy, it's like just a number. And then your accuracy on the right, you can see here, is improving very significantly. I don't know why it stopped, but you can see it's already at like 93%, so it's fairly good. And it ends at like 93.5%. We can evaluate this kind of in the typical way we taught earlier. So we run our evaluation. Actually, it's very simple in this case because we just run model.evaluate. We pass in our test set. And bam, we get a 92% test accuracy. We can make some new predictions. And then we take our third index. All right, this just goes through all of the test data. And basically, it predicts the 6 correctly. So that's cool. Now, let's try this with convolutions. So what we got here is a set of convolutions with I think 32 filters. Oh, we only have one convolution in this case. Oh, sorry, two convolutions in this case. We have first a kernel size of 3 by 3, and then our input shape is just the dimensions of the MNIST image. Where our activation functions are relu. We add a thing called dropout. Don't worry about it too much. It basically just means that like we remove some neurons here and there during our calculations. What? Yeah, exactly. It's like a regularization method, so it prevents you from relying on any neuron in particular. So it's nice. I guess I don't remember the exact terminology, but it's a regularizer term. And so we pass in our train and test data, and then we can just watch it train. Yeah, I wonder if this one's faster or not. Well, the key thing is, even though it may not be necessarily faster on my machine, when you use like specialized hardware like a GPU, you end up seeing like huge amounts of performance increases, especially with the convolutional layers, because it's able to efficiently transform it into the proper space to do all the relevant calculations. So I guess this one takes about like 50 seconds. I wonder how long the other one took. It doesn't say. Oh, it took. Okay. Yeah. So this isn't a fair comparison in terms of the speed, but it does produce much higher quality results. If you let this run to completion, I think it gets to about like 97 or 98%. So a much higher accuracy than the fully connected layer.
Is this
I can add it. This is from last semester.
So is that just because it's a convolutional net? Because if you like a
pulled up a different example that
Yeah.
got like 98%, just making sure to use dropouts on the normal sequential model with 2 dense layers of size 512.
You should, yeah. So you can get like 98% with the fully connected layer, I guess. But I think like the state of the art for MNIST ended up getting like 99.7% or something. If you like Google, like best results for MNIST, it gets like supremely crazy results. Basically, to the point that you're like better at classifying MNIST digits than a human. And so, because a human's going to make some mistakes, as you can imagine. And so we've actually recently surpassed the human ability at identifying like images from the MNIST data set as well. Something like humans get like 5% error or something on average from classifying those images, and they have to be trained. Like you have to like know all the special categories, because there's these like very specific categories like Burmese mountain dog or something like that, and like I don't even know what a Burmese mountain dog is. So okay, I do because I saw the image, but like I wouldn't know it had I not like looked into it before. So yeah, that's pretty much it. I'm gonna push this to the repo. The homework is in the repo as well. If you have any questions, come find us.
See how grades go. Do you have to turn it in?
Yeah, I think we'll be setting up a grade scope for it. It should be fair. We hope to make it as simple as possible. So just try your best at it, and learn as much as you can. And then yeah, be happy that you're not doing this in cafe. This cafe sucks. I like my 100% of my cafe experience happened in the past 30 hours, and it was a pain. It was such a pain. Like, so what I was trying to do was like adapt this paper into TensorFlow because I wanted to use it for this research project for one of my classes, and what happened was I was trying to literally just like go line by line and adapt it straight to TensorFlow, and I realized like there was all this gradient calculation stuff. I realized this after like several hours of staring at it and trying to figure it out, and all this gradient stuff I could literally just avoid by using TensorFlow utilities and stuff like that. Same kind of utilities you can use in Keras, because Keras is actually just a layer on top of TensorFlow for the most part, and so that's cool. Yeah, if you're free to go, you're free to come ask questions.
Is there a quiz?
There's no quiz.
Also, I'm working on grades.